Welcome to Quantum Curious, and in today's lecture, I'm going to discuss a very important and very interesting property of particles in quantum theory. So today is the 40th lecture of our quantum key distribution series. So today's lecture will be going to be very interesting because it's about the most weird uh, concepts in quantum theory, that is the entanglement. And we will discuss that how can we test these highly non-classical correlations between particles through through non-local games. And we will discuss one of the game that is based on a qubit, and it is called CHSH game, and it is based on uh, CHSH inequality. So this is the outline of today's lecture. So first, I will start with the introduction in which I will discuss some basic concepts related to entanglement. Then we will discuss a generic non-local game through which we can test um, entanglement between two particles. And specifically in the last, I will discuss CHSH game that is based on a famous CHSH inequality that was introduced in 1960s. So let's start our lecture. So we know that entanglement is quite counterintuitive property of the particles. So it says that if we try to measure one of the particles in an entangled pair, the effect of the measurement will be felt by another particle instantaneously. And it doesn't depend upon how farther the other particle is from the particle on which we are applying measurement. So this is quite counterintuitive, and this uh, violates our conception about locality. So we know that if we do some action, uh, this is going to be affect only our local surrounding. But uh, in entanglement, if the particles are hundred and or billions of light years apart, they can felt these correlations instantaneously. So this uh, this concept shakes our concept about locality. So the question is that how can we test that? How can we test these kind of correlations? Uh, or whether they are real, because there was a debate in 1900s between Bohr and Einstein about these kind of about on these concepts that are quite counterintuitive and and does not occur in our daily life. So here, so to settle these uh, debates, the John Bell introduced uh, a very uh, important Bell's inequality to test the entanglement between two particles, and it settled the debate uh, between uh, the pioneers of quantum theory that was running from hundreds of years. So that was quite remarkable uh, result, and it says that the correlations between two particles that are entangled uh, cannot be replicated through classical uh, correlations. So this was quite remarkable result by John Bell that he introduced in 1940s, I think, to settle the debate, the debate that was going on about uh, for about the early days of quantum theory. So usually the Bell's inequality is given or explained through non-local games. So we will discuss these kind of games here. So consider we have a non-local game where we have two parties called Alice and Bob, and they have their own boxes called A and B. So the game is about that we have to ask questions X and Y to Alice and Bob, and they will give answers depending upon the questions X or Y, and the answers are A and B. And on the basis of these answers, we have to evaluate whether they have won the game or they have lost the game. So the twist is here that they can communicate or or come up with any strategy before the start of the game. But when the game has started, they cannot communicate with each other. So they have to uh, devise the optimal strategy before the start of the game. So so like any game, there has to be some rules. So the rules are given by this. So the winning conditions is given as this, and the losing condition is given as this. And these are rules for a particular game. And we will see that what kind of rules uh, are these for a specific game. So the winning probability is given as this, and here Pxy is the probability uh, by which the answers are asked, and here is the rules, and here's the probability uh, of Alice and Bob's answers based on the questions uh, that was asked based based on the questions that were asked to them. So we have to come up with a strategy to maximize this winning condition. So as we are assuming that they will think only classical strategy. So the classical strategy they can think of it as this, as they uh, have functions and they put their questions in this function, and the functions will come up with an answer. So here is the function of Alice, and here is the function of Bob, and the function's answer will depend upon the question that are asked by the referee. So in order for this probability is equal to 1, the functions have to give these kind of answers. But that probability of giving answers based on uh, the questions that have been asked by referee to these parties would be 0 otherwise. So here is the twist that we assume that Alice and Bob have shared randomness, and it has been shared between Alice and Bob with some probability PR, and these randomness will be helpful in order to devise some optimal strategy. So our strategy will change according to this, and the probability of giving answers based on the questions will be 1 if the functions are given as this, and they are giving answers according to a randomness and the questions, and it will be 0 otherwise. So the probability now will be changed, and it will also depend the probability of randomness that has been shared between Alice and Bob. So this shared randomness will work as hidden variables, and we know that the concept of the hidden variables. So there is a counter argument against entanglement that uh, each particle has a hidden variable, and the correlations between the two particles uh, are just due to our ignorance, and because we do not know how the coalitions are working together, so meticulously. So we assume that there should be some hidden variables that are giving some correlated uh, results between two particles or between the measurement of the particles. But this kind of conception was cleared by Bell when he introduced his Bell's inequality. So our question is that does shared randomness help Alison Bob? So in this bracket is the winning probability, and we have to devise the shared randomness in or the probability of shared randomness in our classical strategy in order to optimize this winning probability. So we will see that uh, uh, how it will work in the CHSH game. So let's move on the CHSH game. So here again we have two parties, Alice and Bob, and they have boxes and referee is asking some questions, X and Y. So here we have only two questions for each part is 0 and 1, and referee will ask these questions with equal probability, meaning asking question 0 will have probability half, and asking question 1 will also have probability half, and similar for the case for Y, and the answers will be given in uh, in return will be A and B for Alice and Bob respectively. So the winning condition is here. So it is equal to x dot y, that is the dot product of the question that has been asked by a free to Alice and Bob, and here is the XOR operation on their given answer. So the CHSH in probability, the winning probability for the CHSH game is given as this. Here we have 1/4 because each of the answer, if each of the questions has the probability half. So we have to maximize this probability of Alice's and Bob's answers according to the questions asked by the free. So we have classical and quantum strategy. So here the classical strategy. So beforehand, before the start of the game, Alice and Bob can choose that they are going to answer 0, whatever the question may be. So in this case, you can see that the optimal probability of winning the game is 3/4. And if they choose, they are going to answer 1 irrespective of the question that has been asked by a referee. Still, in this case, the winning probability is 3/4, and it is about 75%. So this is the optimal classical winning probability that uh, Alice and Bob can achieve through devising an optimal classical strategy for the start of the game. So let's see what is the advantage of quantum strategy, and can it beat this uh, winning probability of classical strategy? So quantum strategy involves an entangled state, and that is the singlet state, uh, also called Bell state, and it is a maximally entangled state. So the quantum strategy depends upon the measurement. So we have measurement based on the questions that has been asked by referees. So if the question is 0 asked by a referee to Alice, she's going to measure her qubit uh, in standard basis, and if the question is 1, she is going to measure in Hadamard basis. And similarly, for the Bob, if the question is asked by a referee 0, he's going to measure in these bases, and the if the question is asked by referee is y is equal to 1, and he is going to imply measurement in these bases. So these bases are quite optimal, and it depends upon uh, the positions of these projective bases in a block sphere. So for the CHSH game, the angle between the vectors of the bases that we are using for measurement should be pi by 4 uh, maximize uh, in order to maximize our winning probability. So here's the calculations of each case for, let's assume that the questions that has been asked by referee is 0 for Alice and Bob, and here XOR operation should be equal to 0. So in order to do this, they are going to use these bases, and the winning probability for this case is given as this. Again, assume that question has been asked by referee is 0 for Alice and 1 for Bob. And again, we have XOR operation is equal to 0, should be 0 for the winning answers. So again, our winning probability is this. And again, for the other cases. So if we add this winning probability and multiply by it, 1 by 4, that is the probability through which the question has been asked by a free, our optimal probability for this case is 85%, and it is higher than the quantum than the classical strategy that was only 75%. So in that case, quantum strategy is much better than the classical strategy. So through these games, we can test the entanglement between two particles, and uh, if the winning probability is higher, we can say that there is an entanglement between two particles. But if they are mimicking some kind of classical results, let's say we have winning probability of 75%, then we can say that the given state is separable state. So this is for today. We learned that how can we test the entanglement between two particles through non-local games, and how the quantum strategy is different and more effective than classical strategy. So that is for all today. That is all for today. If you like this video and want to share some of your suggestions about improvement or about anything, you can comment below. And if you like this video, kindly subscribe to my channel and like this video.